It's still 2 minutes. Shall we wait or shall we begin? Okay. So welcome everyone. Thanks for joining this session. We're gonna discuss what does it exactly mean that some code is executed asynchronously in JavaScript. And we'll compare 5 different architectures to deal with it in JavaScript. My name is Tomasz Ducin. I design architecture and implement huge enterprise-scale interfaces at Ivanti. It's an American company that creates ITIL software. Frequently I speak at conferences such as this one, meetups, and apart from this I also do trainings on JavaScript-related technologies, and this includes old ES5, new standard ES6, and the ones forward, TypeScript, Angular, React, and last but not least, asynchronous JavaScript, which is the topic of this talk. So we're going to start with recalling the difference between sync, async, and basically concurrency in programming. We'll discuss the mechanics in JavaScript behind that, which is event loop, run to completion, and message queues. And we'll proceed to the main part of this presentation, which is the architectures. So often when I read production code, I see that developers don't really understand the order of JavaScript code execution, right? And this is basically the reason for doing this presentation. This leads developers to do some brute force solution without understanding what is really happening beneath, right? So they try to do some kind of funny tackling that makes the whole situation even more complex and overcomplicated. So let's start with this diagram that shows 3 approaches: the synchronous one, the multi-threaded one, and the event-driven, the asynchronous one. So the single-threaded is the easiest possible approach, and basically hardly anybody is doing it. Here we've got a sequence of instructions. So basically we are doing one sequence at a time, right? A sequence needs to be finished so that we can proceed to the next one. If the code depends on what we're doing, like we want to increment a value, we want to create a new memory frame or whatever, we can do it immediately. The problem is if we need to wait for something, right? For instance, if we want to open a file or if we want to shoot a request to something that is external, we need to wait for a disk operation, I/O, or we need to wait for the server response, right? So in this approach, we need to do things step by step. So if we need to wait for something, we're just locked, right? We can't do anything by this time. So so hardly anybody is doing it for this reason. So one possible approach to deal with this problem is to create several parallel threads, right? Each of them has its own logic, and they share the same area of variables, the same area of data. This solves the problem of waiting, right? Because if one thread is about to wait for something, then the other threads can continue their work, right? So the problem is solved, but different problems are introduced. So they all have different logic, but they share the same variables. So what happens if this one goes too much further comparing to this one? They can just, tackle get in conflict with each other. So we need to have semaphores, we need to deal with deadlocks somehow, right? And this is difficult, especially in terms of debugging. So another approach to deal with this is asynchronous. So we're going back to a single thread. So again, there would be only one thing executed at a time, right? And there needs to be a mechanism that will deal with operations that we need to wait for. So basically, if something is dependent on us, we are executing all the code until we find something that we need to wait for. So we kickstart this operation, we just move it back, and we'll do something else. And there would be somebody who will tell us, okay, the thing is ready, just go back to it. And this is where event loop is going into the picture. This is somebody who will tell us that another task is ready to be executed, right? So this is very important to to distinguish. Actually, most of the code in JavaScript is somehow synchronous and asynchronous, like it's a mix. JavaScript is asynchronous first language, but it doesn't mean that everything is asynchronous, right? So it's only some pieces of code that will be cut out from the main execution line, and they will be just executed later. And we will see how this works. So comparing sync to async, the first thing is that synchronous is blocking. So if we've got an operation that we need to wait for, we are just locked. We cannot do anything in the meantime until this operation is ready to proceed, whether asynchronous is non-blocking. And as a result, synchronous code is linear, right? So if there is an operation at the top and there is operation at the bottom of our code, then we are absolutely sure that this reflects the code execution order, right? It will always be executed linear. Whereas in asynchronous operations, that is not linear, right? So we will be jumping, right? The code execution will be jumping through the code entirely in our application. So when I try to explain asynchronous approach, I strongly believe that the best way is to learn by metaphors, but not metaphors that relate to technical systems and especially software engineering, but especially like real-life metaphors that relate to your life, relate to your family, your trips, journeys, vacation, whatever. So I would like to ask you for just a few examples of something that is asynchronous, like in your real life. Go on. Could you make it more precise?
For example, you're waiting for the hot water for tea.
Yeah, exactly. You're waiting for the hot water, and we will have this example later in the slides, by the way. Okay. So this is the example. So let's say we've got a kettle with boiling water, and we've got a box with tea bags, and we want to make us some tea. So what I would do is I would just pick up this kettle, I would pour water inside, turn it on, and then, yeah. And this is the best way to understand the real difference, right? If I was synchronous, I would freeze, just wait until this kettle is done, like waste of time. Then I could just reach this box of tea, then continue, right? But what humans do, humans are really very much asynchronous. We're not parallel because we don't have like multiple brains, right? We're just, we're doing like, unless somebody can do one thing with one hand and the second thing with second hand exactly in the same time, but I don't expect this is easy. So what I would do is I would set up this kettle, I would just put it aside, right? I would do something else, grab this tea, and then I would just make the tea, right? And yeah, one more example. Relating to breakfast. Let's say I am waiting for a very important call. Somebody wants to call me, let's say, related to my job or whatever. And I just came home, I'm hungry, so I prepare myself toasts. I start eating the toast, and during the task of eating the toast, the phone is calling. What would I do? Stop eating. Okay, this is what I would probably do, but it doesn't matter. So if we have two possibilities, right? You mentioned that I would interrupt the task of eating toast in order to handle another task, right? So this is a task interruption because picking up the phone, answering the call is more important than the task of eating toasts, right? There is a relation that a task is more or less important than another task, right? So we've got two models. We've got cooperative concurrency and preemptive concurrency, right? What we deal with in JavaScript is cooperative concurrency. All tasks are exactly equal, like in communism. Nobody is more important and nobody is less important, right? So if I'm eating a toast, I will fucking finish eating this toast until I can do anything else, right? This is critical, this is fundamental to understanding concurrency and asynchronicity in JavaScript, right? An example on contrary of preemptive concurrency is, for instance, operating system, right? There is a scheduler in operating system that knows that some tasks are more important than the others, right? If a more important task comes in, it will just, it will move away the less important one and give time and the power for the more important, right? This never happens in JavaScript. As a result, if we schedule a task that is big, right, it will go to the message queue, will be handled by event loop eventually. There is no way to cancel it, right? This is important. So we've got an example here. This is a bathroom queue. Assuming that people are gentle and nobody wants to brutally force this queue, this is a cooperative concurrency, right? It's a FIFO, first in, first out queue. So if somebody came here, right, is just very, very close to the door, then there is no possibility that somebody will just, walk aside, right? And this explains the reason that set interval and set timeout do not guarantee exact time in JavaScript, right? They guarantee, what do they guarantee? At least, yeah, they guarantee at least. So it means that if we schedule something with set timeout or with set interval, it means that at least this amount of time will elapse. But if there is a task, ongoing task, it cannot be moved away, right? Because it's cooperative concurrency. This is the reason that it will have to wait. So this is cooperative concurrency. Another result of this is some UX performance issues. Let's say that we have an AJAX call that will receive a lot of data that we need to process, we need to do some calculations, or we need to display some DOM nodes. Like this will be an operation on thousands of nodes that will take, let's say, several seconds, right? We can experience a situation then when we have this call answered, the browser will freeze for several seconds, right? And do you know the reason for that? Basically, there is one task, right? There is one task that cannot be interrupted anyhow, right? And this is another rule that that is called in JavaScript run to completion. If a task has been started, there is no way to interrupt it, right? There is no way to handle anything else. JavaScript is single-threaded, so event loop will be taking one item at a time, executing this thing. And just after it has completed this single thing, it can take another thing, right? So what we can do with such situation, if we have a very long and very big processing operation sequence? A very simple solution. Exactly, cut it to pieces with set timeout or set interval or any other solution. Basically, having one long sequence of operations, we just need to cut it, right? So that each of them becomes a separate block, each of them becomes a separate message on the message queue. We will see a simple animation of this. JavaScript is both object-oriented and functional, somehow functional language. I would say strongly that the functions is the most important and critical piece of JavaScript. In order to understand what is going on in JavaScript, it would be nice, but we don't have to understand the objects, the prototypes, ES6 classes and this kind of features, but we really need to understand scopes, closures, context binding, legacy features such as hoisting, the immediately invoked function expressions, and the new functional programming paradigm, including side effects, pure and impure functions. This is the core thing. If you don't understand this, don't write JavaScript production code, please. This is the core thing, and we will start with this. So the first critical thing to mention is we need to realize which functions, which callbacks are executed synchronously and which ones are executed asynchronously. So a simple example of a synchronous callback is for each, map, filter, find, and other functions like this. So basically, if I would have some code like above this, I would just execute the code above, go inside, exactly immediately, right? Without event loop at all, and I would just walk further, right? As simple as this. And in case of set timeout, synchronously, right now, I would register this function somewhere deep in the browser, and I would just walk further. This function is not going to be executed, right? So this also explains the reason for having set timeout 0, which is doing quite a difference, because the function that is inside is not going to be executed after 0 milliseconds timeout. It's just being put onto the event loop, right? And then when the event loop is ready, it will just pick it up, right? So it changes the logic quite significantly. So having this snippet of code, we've got a list of 3 items and a bit of console logs here. What is the console output in this example? Yeah, exactly. It's before, 1, 2, 3, and after. So we are doing everything synchronously, like linear execution, right? And in this case, yeah, before, after, and inside. So when we read code, it's good to have some kind of, you know, an eye feature that will spot all places that are asynchronous, right? We can see that this is a set timeout, right? This is asynchronous function, so we can cut it, right? We cut this function out, and we can see that it will be pushed into the message queue, right? It will be executed later, and we don't exactly know when later, right? Because the time is not guaranteed precisely, it's guaranteed only at least, right? So each asynchronous thing, whether it's timers or HTTP or events, browser events, it doesn't matter. Each of them creates a message on the queue, right? This is a simplification that there is just one queue, because browsers have at least 2 queues, and depending on implementation, it can be a lot more. But let's say there is just one queue. A single block is just a single message, which is what happened. It was an interval, it was a HTTP REST API request, whatever, and the attached function callback, right? So this is a first in, first out, and when all those things are ready, event loop is just picking one item at a time, putting it on the table, executing this. Once it has been finished, it's thrown out, and another thing is just taken away from the message queue and executed, right? So it also depends on when do these messages arrive to the queue, but we'll talk about this in a while. And remember, JavaScript is single-threaded, so there can be only one message executed at a time, right? And also that these messages, this is just an information on what happened and the function callback. This block will not know where did it come from, right? So if we had quite a bit of functions deep down that call this set timeout, we will not know how did this arrive here, right? So if something is asynchronous, we lose this information, right? So sometimes we will not choose the asynchronous approach. We will see this in events, and we will pick the synchronous approach because we do have all the information about the call stack, right? This might be easier. And the last thing here, event loop is not the same structure as message queue, right? Because if things were being pushed directly to the event loop, the order of execution would be slightly different than it is. These are different structures, right? This is important to remember. Okay, so let's look at this code right now. It's just another bit of console logs, not to explain too much. The question is the same. What is the console output here? Come on, don't be shy. Could you repeat? 5, 2. Not really. 1, 4, 5, 3, 2. Yeah, this is the good answer. By the way, it's not an interview it could be an interview question, but the important thing is not what is the result, right? The important thing is what you know about the asynchronicity model in JavaScript. So we already said that callbacks might be either synchronous or asynchronous, right? Somebody said that there would be 1, 4, 3, right? It can't be done this way because this funny syntax structure here, the IIFE, immediately invoked function expression, it is executed synchronously, right? Immediately, like this. So I could remove those things and there would be no difference. We use IIFEs not to pollute the global scope, right? But it's just synchronous. In terms of execution order, it has no difference. So what we're doing is we are synchronously. We are executing console log, so there is just one. We are registering the callback, this one, synchronously, right? Then we proceed to register this callback synchronously, right? Now we are console logging 4, then we console log 5, and then, yeah, we're going back to run to completion. This is the first message that was on the message queue, right? Now it's completed, right? We've got also 2 more messages. This is the second message that will be executed later, and this is the last one executed later, right? So the thing I would like you to remember after this presentation is try to cut the code in pieces like this, so that you will see how do they reach message queue. And just one more question, or maybe we can talk about this during the break. Would there be any difference if there was some operation here that lasted longer than 1 second? Would this affect the execution? Yeah, if there was some kind of synchronous operation that would take more than 1 second, would there be any difference? So we can talk about this after the break because we don't have, basically we don't have time to speak about those things, and I'm afraid we'll have to rush a little bit anyway. So let's carry on. The last thing, last fundamental thing about asynchronous operations, especially when we talk about external stuff like web services, WebSockets, AJAX calls, is that the order of their execution, of their arrival, is completely unreliable, uncertain, unstable, inconstant, and so on. Like any adjective is suits here. We cannot make any assumptions, right? Because if we do otherwise, if we make any assumptions, then we do race conditions, right? So we will see an example of a race condition here. This is an AJAX call of whatever library this is, doesn't matter. We're shooting get customers, an AJAX call, and once this data arrives, we attach this to the customer's variable. Usually the call takes half a second, right? Just always when we try to shoot this call, it takes the same amount of time. And there is another call that takes 2 seconds, and it's products. So here in the callback, we do have customers already inside this variable, and we have the data, which is the products, and we want to manipulate them, to process them, having both, right? And this is the later, this answer comes later, right? So we are doing some kind of assumption that this will be the first one, this will be the second one. It's quite obvious what happens if it's otherwise, right? And it's quite obvious that it can be otherwise because of some network latency, the server being interrupted or being busy, right? Just some small pick might reverse the order, and then everything will collapse, right? So we can never make any assumptions on the order, right? We need to design the logic of what operations need to be in what order, but never like this, right? And we'll use promises for that later. So we've already covered the first architecture, which is actually no architecture, which is just pure callbacks, right? But callbacks will be used throughout throughout the rest of the presentation and basically everywhere in JavaScript. The second approach is events. We can have browser built-in events. So this is basically everything that the user can interact with the browser. So it's click, focus, blur, moving the mouse, changing inputs, changing the values. So this is a simple code in jQuery. We get a selector, an element, and the browser handles triggering the events on these elements. We just need to listen on them, right? So we attach an event listener, and each time this event is being triggered, this function will be executed, right? So event is something that is used multiple times, comparing to promises, right? Which are just disposable. They're just one-timers. So these are browser events, and we don't really know when will the user click on a certain thing or when will the mouse move. So we call them that they are asynchronous, right? What happens beneath is just one click, one event is just being pushed onto the message queue, and it's just awaiting execution, right? The events bubble, so it's just checked how many callbacks are attached to a given event, and if there are any event listeners on the parent of this node, right? So for each of this callback, there will be just one message that will be moved to the queue, right? So this is quite simple. There are also custom events, right? So instead of saying that a user has clicked a button, we would like to have an event that a user has been added to the system, a user has been deleted from the system, or that some money was transferred to another user, right? So some kind of domain events that an information is consistent for the event. So using jQuery, we still had to pick an element, right? To trigger a custom event from this element and to have another element listening to it, right? A DOM node, which is pretty limiting, right? But many implementations that were using jQuery beneath just created some kind of abstraction on this. So in Backbone, for instance, we could trigger global events, like in terms of the whole application, or we could just choose a single view to trigger the event, right? But the thing here is that these events are executed not asynchronously, but synchronously, right? The reason for this is that if there was a set timeout 0 here, so it would be just pushing a message down to the event queue with no delay. Like when JavaScript will be ready, it will handle it, but we will lose the call stack. We would not know how did this thing reach this point, right? So thanks to the synchronicity, we know why is this thing happening, right? And this is a lot more benefit than having it asynchronously. So this is the second approach, which is called event-driven architecture. The event-driven architecture is about composing components that will listen to some kind of events and will trigger another kind of events, right? So they are pluggable. If I put a new component, it could trigger events, right? And it doesn't matter if somebody is listening to them. On the other hand, there might be components which are listening on events, and it doesn't matter if there is anybody triggering these events, right? So they are easily pluggable. Like I can inject it, I can remove it, right? The problem with this architecture is that events are being pushed in all directions, right? There is complete chaos. It's difficult to debug, it's more difficult to test, and React one-way data flow is doing it easier to maintain because the data is just being pushed in one way, right? The props are going from the parent to the children, right? There is just one way, and the user interaction is bubbling up. So there is always one way. In event-driven architecture, all events are going always. So this is more difficult to deal with. Okay, so in terms of both callbacks and events, we are suffering from one particular problem here. This is a Node.js code that is executing some SQL calls, but it doesn't actually matter. After this call is executed, we want to do another thing. And when this another thing is executed, we want to do another, and finally, there is still one another thing, right? This is called the callback hell, flying V, or pyramid of doom. You can see like maybe some more names of that. But basically, if we want to get to step n, we need to work as a compiler and to see what is the indentation, right? Assuming that there is either only spaces or either only tabs, right? This is really difficult to work with. So having this problem in mind, JavaScript has introduced, the JavaScript community has introduced an idea of a promise, right? How many of you are using promises? Okay, most of you, good. So a promise is an object, right? It's a promise that a single operation will complete in future, right? So let's say, say that you'll give me, let's say, $1,000. Could you say it for the sake of this presentation?
I will give you $1,000.
Okay, you heard him. And he made a promise, right? And now there are two possibilities. He will either fulfill the promise, he will give me this, we'll see, or he will reject the promise and he will just say no, right? So although there is something promised, it's still not sure if this will happen or not, right? From code perspective, there is always a function that will return the object of a promise. We can register, just like we did with set timeout or with the events, we just register that there would be another step and it will accept a callback function, or there would be a error handler in terms of catch, right? This might be something that is built into the browser or a custom operation, right? A promise has three states. The first one is pending. When you said, I will give you $1,000, now I'm pending, I'm waiting, right? I don't know yet. So this is my state of pending. And when you give me the money, right, this will be fulfilled. There is no going back. And if you reject me, there is also no going back. Once the state is being settled, it can't be modified. What will happen if I try to brutally modify the state of a promise that has already been settled? Come on, sometimes you have to do it in the code. A promise that was once settled, you try to reject. What will be the result? It'll just be ignored, right? So in ES6, if you write, let's say, a constructor promise that will randomly either succeed or fail after a timeout, and there is a race on the timeout, the first one will be accepted, the second one will be ignored, right? So let's say that these async operations, operation 1, 2, 3, and forward, they're just returning promises, right? So we've got a promise here. Each promise returns another promise, and a promise has always then method implemented and catch method implemented, right? So this then still returns a promise, so we can chain this. And comparing to the code we've seen in Node.js just a while ago, we can see that this is just a step-by-step, like linear, somehow linear operations, right? Linear manner of writing, right? We can see what is going to be the order of them, but they're obviously asynchronous. There is one more thing, that the output of operation 1 becomes the input of operation 2. The output of operation 2 becomes input of operation 3, so we can do a pipe, right? Often we don't do like just processing because it would not make sense, but often we do this when there is any kind of asynchronous operations. Like we fetch one data and we need the result to shoot another request, right? This is what we do. So this is a promise chain. What we see here is actually sequential processing. So we shoot the first request, the first operation. After this operation is done, we can proceed to the second one. This one has to be finished so that we carry on to the next, and then the next. We can wrap it in a function just like we did with the sequential, and we have to return this thing here. This is critical if we want to use it outside, right? Sorry. if we want to use it outside. So we just call the sequential function here. It returns a promise. Each promise has then, so we can make this kind of processing, asynchronous processing, reusable, just using a function. On the contrary, we've got parallel processing, right? So here we are synchronously starting the operations. We are just storing the promises in the variables, and we are executing the promise all aggregate operation. We will see aggregate operations in a while. So what happens here? I am synchronously starting these operations, not waiting for them to finish, right? By the time I'm here, all the operations has started. Maybe some of them are finished. I don't know, because this is outside of my scope. This is outside of our code, right? And this promise all will gather all of these operations and merge them into a final, into a single promise, which I can obviously use somewhere outside. And these two patterns of sequential and parallel processing are the key to combine bigger business logic in our daily work. So we have covered promise all. Can you give me an example of a promise all? A real life example. Okay, real life example. Okay, so what happens here is that we have a list of promises, as you can see here. The condition for promise all is that they all have to be resolved positively. They all need to succeed. If there is at least one that failed, right? For instance, P2 has failed, then the condition that they all will succeed is already impossible, right? So we reject the whole promise and catch will be executed. So let's say that we have P1, P2, P3, P4 pending, not known yet, right? P1 is succeeding, then what happens? Nothing yet, right? Because not all of them have succeeded. But if P2 has failed, then the whole thing fails, because it's not possible anymore that they all will succeed. Give me a real-life example of this, please. Sorry? Yeah, but having a tea or not is not really asynchronous. But it's still synchronous operation.
So when you prepare the breakfast and you're waiting for the eggs to boil and the water to boil.
Okay.
And then you can eat the breakfast.
Okay, if it happens that your kettle goes down, right, you still have eggs. Yeah. Does this make you not to eat them? This is very important that we the programmers are very positive. we're too much positive. Always consider the failing scenario. Let's say that you don't have tea, sorry, the kettle exploded, but you have the eggs. Would you eat them? Yeah. I would. Why not, right? I would just drink water, right? So this is not a good example. You need to find an example that if any of these fails, the whole thing is not possible anymore.
Maybe something like building a car.
Sorry? Can you raise your hand? Oh. Sorry.
Building a car.
Yeah?
When you need to build an engine, some, I don't know the name of other parts of car,
yep.
But you need some glasses, some doors,
Mm-hmm.
and if you don't have all parts, the car will not be ready to use. But you can replace the broken parts. So.
Yeah, but this is a it depends whether it's a synchronous or asynchronous operation. If they were asynchronous, then okay, because you need to have them all. An example that seems quite clear is we want to go on a vacation, right? We are planning vacation. We need money, right? Because we need to pay for the accommodation, for the food, for the transport. We need to have the accommodation ready somewhere because we have to sleep somewhere, right? Obviously. And the third thing, we need to have some time off at our work. If any of, and we need to apply for this somehow, right? We need to save money. If we don't have, we need to ask for having days off. If any of these things fail, the whole thing fails immediately, right? And we blame that the reason was, right? So it's always good to think of of a real-life example of what happens. This gives really better understanding. So another aggregate is Promise.race. We've got list of promises. The condition here is that the first one that settles, whether positively or negatively, will settle the whole promise, right? So if the first one settles positively, the whole thing resolves. If the first thing fails, whichever of these, the whole thing will fail as well. Can you think of a real-life example of this one?
You're a taxi driver and you see your clients that are running to you, like you have 4 clients running simultaneously. Whoever gets the cab first is like going to drive.
Okay, so, sorry. This is, again, very positive thinking, because you are doing a race on whoever is first. But let's say the first guy, the one that is running the fastest, is just breaking his leg and he's falling down. He rejects. So this means that the taxi will say, sorry, rejected. Everything gets rejected.
Like only one can like get into the cab.
Yes. Imagine all those 4 are pending. The first guy is breaking his leg, and he's rejected, so the taxi journey is already rejected. This is Promise.race.
Basically, the thing is that what is the acceptable state? And in our case, for the taxi driver, the acceptable state is that someone gets into the cab.
So it's a promise that never fails, a promise that never rejects.
From the taxi driver perspective, yeah.
Believe me, it's not a good example. Actually, this is freaking difficult to find in real life, but after some thinking there is, I would be very happy to discuss it during a coffee, during a break. So, these two are implemented in ES6 standard. It's a very funny situation that race came here because there is not so many use cases as we would expect for race, comparing to any that is implemented in Bluebird. We can easily implement this one ourselves, or we can just use Bluebird. It's by the way, it's a very good programming exercise to try to re-implement all these aggregates using functional approach or imperative approach, whatever you like, just to try to understand how these things are working. So promise any is, again, accepting a list of promises, and it just needs any of them, one single promise to resolve, to have the whole thing resolved, right? So if P1 is failing, then one item can still resolve. P2 is failing, so 2 items failing, 2 pending. There is still a possibility that something will resolve. The thing will get rejected once all the promises are rejected, because the condition that at least one will resolve is not possible anymore, right? This is quite easy, right? You can also think about real-life situation of this. This is a good exercise. And finally, Bluebird promise.sum. This is a more generic example of promise any. Promise any is sum with parameter 1. Promise sum is just at least n promises, 2 in this case, right? Having understood all and race, I hope that any and sum are easy or obvious. Raise your hand if it's easy right now. Okay. Quite good for a start. Okay, so there are lots of patterns and problems related to promises that we didn't mention, like splitting, joining, error handling, end-time patterns like broken promise chain, deferred itself is an anti-pattern, and jQuery 1 and 2 promise implementations that are broken because they are not synchronous. They're releasing the Zalgo, but this would require another 15 minutes. And referring to previous steps. Promises can process one item, right, in a pipe. So what if we want to refer to an item that was not in the previous step, but let's say 3 steps back? We can't do it any easy way, right? We need to do some kind of hacking around. So we have covered promises, which is absolutely fundamental thing. I'll just see the time. Oops, this is going to be difficult. So we need to speed up. So we'll introduce generators to combine them with promises to see coroutines. So we have a function that has 3 elements, right? It's just a static array. We have all the elements here, right now. They're already in memory, right? A generator is a new kind of function introduced in ECMAScript 6. It's a function that can be paused. It can be freezed, right? It's not finished yet. It's just paused and can be resumed at a later time. It's a completely new world in JavaScript, which opens lots of new possibilities, and coroutines is one of them. So we have a function, like you can see that instead of return, we've got yield. So yield is just a single, returning one single value, but it's not terminating the function. It's just giving one function, one item and freezing. After this, the outside world can ask me to revoke, right? To execute back. ES6 also introduced the for-of iteration, which uses the iteration protocol. So basically, it doesn't matter what are you iterating over. It can be an array, it can be a map, it can be a set, or it can be a generator, and it is just going item by item, right? So we say that the static data is greedy because we need to load entire thing into the memory. Whereas in generators, we have only one thing at a time, and this is the amount of memory that is allocated. So imagine that we don't have 3 elements, but 3 million elements. In this case, a lot of memory needs to be consumed. Here, only one item, right? This is the power, this is the great power of generators that is really, really important in terms of Node.js data processing and in terms of combining with promises to gain better synchronicity. So yield is basically just a road sign in the US. If there is somebody from the from the road next to you, you need to like give them the control, right? So you give the control back, but you will be revoked later afterwards. So this is a simple example of a generator, right? Here you can see the asterisk and yield, right? So we create the generator, we do the outside console log, right? Then we do next. This like opens the generator. So it does console log 1 inside and yield A. Yield A is not used here, right? And this generator is going to be paused. So we do console log 2 outside, then we do iter next. So this guy here is resumed, right? And he does his stuff until he finds the next yield statement, right? Then he pauses back again, right? Now we just do console log 3 outside, right? So this is a function that can has whatever logic you want it to have, and it can be paused and resumed. So this is a very simple thing about generators, and now we'll combine them with promises. So promises plus generators is what we call coroutines, and it will be called async await in ES8, which is one of the most wow features in the ES6. So a promise is something that is asynchronous, it's non-blocking. So we start an operation that we will be awaiting, right? But we want to do something in the meantime. So basically, we will pause the execution because we're waiting for the thing outside, right? So when the promise resolves, we will just resume the generator, right? Or if it rejects, we will inject the error into the generator because we can do it. We didn't mention it, but we can do it, right? And we can just proceed to the next step. So basically, we take promises with all the aggregates we have, and we just wrap it with the generator, right? And we also need to wrap it in some kind of execution environment that will be doing all this stuff, right? Having understood promises and generators, coroutines should be very easy. So we are doing one more step to achieve asynchronous code, asynchronous execution written in more synchronous manner, right? So we get back to the same example that we've seen before, the sequential processing. So we have 4 operations that we will wrap in a function, right? So here we need to add the asterisk, and here we are doing yield here, right? So what this function is doing, always when we have an assign operator, first we calculate what is on the right-hand side, right? And then we assign it to the left-hand side, like in all languages we do the same. So we do async operation, which is a promise, and we yield it. So we wait until it finishes. If the promise is pending, The generator is paused, not doing nothing, because it's waiting, like it makes logic, it makes sense. So once it has resolved or rejected, this will resume the generator, right? So we do it step by step, so we stop here, we stop here, we stop here, and we return the promise here, so naturally we stop. The only thing which is like quite messy is that we need to have some kind of, let's say, this coroutine environment that we need to wrap the function with. This is the async function here, but let's not talk about this right now. So this is just another thing. Obviously, the slides will be put on Twitter, so just follow me to get the slides later. So this was sequential processing. Now let's get to parallel processing. So here we are doing exactly the same thing as we did before. So we are just starting the promises, storing them, starting the operations, storing the promises in variables. So we do return yield 1 plus yield plus yield plus yield. The thing that is happening here is that we are still waiting for all of them to be finished, right? Let's say that in this case, this is just adding the values like integers, but it doesn't matter. It could be any other kind of processing here. It would work exactly the same. And this returns a promise, so we can listen to it and attach another callback. So this is coroutines, and this magic couple of lines that do the right thing, this is the implementation of the async function. But actually, don't read this, please. It's not important because we already have async await inside the browsers, inside Chrome, right? Async await is just implementing this internally in the browser, right? And doing just a small modification. So this is a snapshot of just made few days of what we already have accepted in ES in new upcoming ES versions. So we have async functions arriving in ES8. You can see them in Chrome. So what async await is basically, this is just coroutines, so it's promises plus generators, is exactly what we've said already. But instead of the asterisk here, we do async, and instead of yield, we do await. Everything. This is async await, right? And this is one of the coolest feature in JavaScript since promises, including generators. Generators introduce a completely new way of executing code. This is a deal breaker. So this is async await parallel processing, right? So we're just awaiting these operations. Await is like yield, is the moment that you need to stop. And on the other hand, we've got parallel processing. So we start all the promises, right? And when they're all available, we can just merge them and wait on this piece. If you don't make it to do the photos, you can just follow the slides. Everything will be there. Okay, so we need to hurry up. There is also CSP, communicating sequential processes. So a coroutine is a encapsulated logic of an application, right? That will be executed, paused and resumed, and paused and resumed asynchronously. Now imagine that you have several coroutines that need to talk to each other, but still they are in a single thread environment. This is CSP. This is a coroutine is just named a process, and they're just communicating between them sequentially, right? Sequentially because it's a single thread. And we will see an example. JS CSP is just a library that implements it. I'm sorry, but blah, blah, blah. Go starts a coroutine. Channel is just a channel that these processes will be communicating to each other using it. Yield take is a process is waiting to get a value from another process through a channel, and yield put is putting this value into a channel, but it will be blocked if there is nobody either accepting or giving the value on the other side. So if I'm putting something and there is nobody listening, I'll be blocked. And the same thing for take. So let's see a very complex example. Basically, there are just two processes, 1 and 2, talking to each other, and there is a console log here. Don't read it right now. We will go step by step. We've got process A and process B. So we are starting with process A doing yield take. He's trying to take something, but the other process didn't put anything. So this one gets blocked. So process B is given the execution, right? So it's console logging what is sending, right? So console log appears here. He is putting the value into the channel, so that guy got unlocked, and it's taking the value from another channel, and there is nobody there, so this guy is blocked, right? So the execution is handed over to process A. So we've got a console log received, which is console logged here, and we're going further. We are giving another item, console log sending cat, and we are putting the value into the channel B, so we unlock this guy, but he is still working, right? He is unlocked, but he didn't finish. And he goes to take, and nobody is giving the value, so he is locked. So the execution is handed over to B. So I'm receiving the value because I just got unlocked. I log it out. I proceed. I do another item, sending wet. And finally, I do the put. So I unlock this guy, and I finish, right? The process B got finished. And finally, there is still one process running that is unlocked. So I console log, I take the value, I console log it, and it's here. So this is how we can do communication between coroutines or communication between async 08. I believe this is going to be a very strong thing in Node.js processing. I'm not really sure if it's going to be that strong in browsers. But we will see. This some kind of presumption. Difficult to say what is the future going to be. And the very last thing that we have no time for. So let's say that we have a function that processes an item. For a given item, we multiply it by 2, just to make it as easy as possible. And we have static data, right? So we have all the data here. And contrary, we have a stream, right? A new thing. And we are getting to reactive streams. So here we've got everything already, all data available, so we can process it all. Here, on the contrary, we don't have the values. Maybe they don't exist at all yet, right? So here we will just synchronously grab each of them and process it and return another value, right? It's a map. However, here, whatever item gets into a stream will get processed, and maybe there is a subscriber listening to the thing, right? So we will be either synchronously or asynchronously putting the items into the stream. So here everything is in memory, and here in the streams it can be either synchronous or asynchronous, right? Actually, it doesn't matter, right? It doesn't matter whether it's synchronous or asynchronous, at least in order to understand Rx. Don't think about this. Think of a stream. You push an item into a stream, right? And there will be some kind of pipeline. And somebody needs to subscribe to it, right? So Rx is reactive streams. It's reactive because we react. We react, not JS, we just react. So we, instead of pulling, instead of asking for data, we just push it into a stream and everything goes automatically. And what we do is that we subscribe to the stream, right? So for each item that went into the stream and went through all this processing, there would be just one function, callback function for one item, right? So event is multiple times, promise is a single time, and going back, Rx is again multiple times, right? For a promise, you can just do one thing, right? If you want to repeat the whole thing, you need to create another promise, right? With events, it's handled by the browser, and with Rx, you just get it handled by the library. So for the functional programming operators, we do manipulate the data, right? On the other hand, for reactive streams, we do manipulate the data, but we also manipulate the time, right? When do we push the items into the stream? So this is a nice animation just to show that Rx is the same for all the platforms you would be working with. This is a nice comparison written by Andrew Stoltz, the author of Cycle.js, which is built on top of Rx. He states that promises are always async, and they should be because this is built into the specification. Observables, however, the streams, are either sync or async, and this is not that much important in terms of them. A promise can always have only one value, whereas an observable is multiple values, right? Promise is always eager. If we set up a callback, there is no way to break it. We can wrap it with arrays, so when something rejects, the next steps will just get cancelled. But if we set up one promise, there is no way to break it. And observables are lazy. If we don't subscribe to a stream, it understands its own logic, but it just doesn't execute. Because why, if nobody's listening, right? And promises will always do the thing. And finally, promises, I already saw that, can be cancelled and observables can be cancelled. So in terms of a promise, for a single promise, we can register a then positive callback or a catch, which is the negative fail callback. And this is just one timer. For observables, we do subscribe with 3 functions. On the next, which is execute the callback each time for each item, right? And a stream can be completed or failed, right? So it means that the whole stream, doesn't matter how many items there were, it will either complete, so we expect no more items, or it will just fail and it's just failed, right? So 3 fundamental pieces to understand in RxJS. What is your data source? It can be a click, right? It can be just browser events. It can be an interval. It can be your custom logic. It can be whatever you use. Then we've got processing items. So this is all the functors like map, filter, find, and 1,000s or even millions more. We just process the items. And we've got the observers. So the things that will react to the items being pushed, right? So a click is used. This click is just a stream. So we create an observable from an event, just clicking wherever on the document. We attach map and filter just to process the events so that we have the events, the items having the X and Y coordinates, and we filter them to be only on the left-hand side of the screen. And at the end, we've got the subscribe, right? So we react to each item that is here, we just console log it, and we do some other console operations on error or on completion, right? So this is very, very like the first minute of RxJS. This is the most fundamental things. Some people ask, what is the difference between Rx and the observer pattern, right? This is a very valid question. The answer is that Rx is observer plus iterator because we iterate over items, right? And plus functional programming, because we do it in functional programming approach, functional programming paradigm, right? So, just to sum up, the most fundamental thing here is the function, right? You need to understand the functions in JavaScript in order to proceed. You need to understand that they can be executed either synchronous or asynchronous way, and that we have event loop, run to completion, and message queues inside the browser, right? Then we step to the architectures. The first one, callbacks, and the one related is events. Next, we've got promises. When we combine promises with generators, we get coroutines, which is pausing a generator when we are waiting for the asynchronous operation to finish. If we have multiple coroutines, then it's communicating sequential processes. So it's single-threaded coroutines talking to each other, right? And the new name is async await. Async await is just a new name that makes the thing more handy. And finally, something that is from the other world is reactive streams. So I hope this gives you a better understanding of the whole picture. So this is all I've got. Thank you very much.